Shweta Chanda. I am a PhD student at IIT Delhi under UQ IIT Delhi Exchange Research Studies. So I am the TA for this course. Uh, Let us begin. If you have any doubt in any portion of the this tutorial, if you are in a live class, you can ask here in the comment box. Also, if you are watching it later in a YouTube video, so you can comment there also, or you can ask the question in the forum. So it's past 3 minutes of the scheduled time. So let us begin. So first, I want to start with some revision of the class of first week. So I hope you have gone through the classes or lecture videos explained by the professor very well. But still, I want, for mathematical question solving purpose, I am still writing some basic equation as a recap of the classes. So first I am writing 1D wave equation. So we all know this is the 1D wave equation. And the simple solution for this wave equation is function of x and t, which is in the form of f of x plus minus vt. So we know the positive sign like denote that the wave is traveling in positive x direction, and negative sign denotes the wave is traveling in negative x direction. So this wave wave equation can be written in terms of electric field wave equation also. So the electric field wave equation is being written zero. So V is basically 1 by root over mu epsilon. This is permeability and permittivity of the medium. If it's like wave is propagating in a vacuum free medium, then it is C, vacuum free, or like in the ideal medium. So we assume that it's propagating with the velocity of light. So C is equal to 1 by root over mu naught epsilon. So the simple solution for, let us put the name to, and this should be 1. Or equation can be written as can be written as this, and we can write this equation as a cos kx minus omega t minus theta. Theta is initial phase of the wave. So how we can write this identity as this? It has been discussed in the class. So basically, what is k? K is a wave vector, which is 2 pi by lambda. Lambda is wavelength. Omega is angular frequency, which we can write as 2 pi f or 2 pi mu. F or nu is a circular frequency, or mu, which can be written as 1 by t. T is the time period. And V, we know we can write this as a 1 by root mu and epsilon. It can also be written as omega by k and also lambda nu. So we know that we call this thing kx minus omega t minus theta as a phase. So this thing is phase. So if we take a partial differentiation with respect to x, we get k. And if we get a partial differentiation with respect to t, we will get minus omega. So we can write v as t minus by. And if the phase moves means the wave moves a distance d in time t, or frequencies mod t. This is not time period here, remember that. So the delay will be written by d by v, which is the phase velocity. So in the class it has been already described why it is called phase velocity, not wave velocity and all those things. Later in the you will understand that in general, in real life, not only one wave travels. The wave travels in a group or packet, then we will discuss the concept group velocity. So phase velocity means like the phase of a particular wave, the velocity of a phase of a particular wave. So when I say a phase moves a distance d in time t, that means the phase of a particular wave moves a distance d in time t. So the phase delay would be d by v. So we can write phase delay in phase at x plus d distance at time t minus phase at x position x at time t. This is kd and or omega t. Now I want to write some solution of wave equation. So we know we have written the solution, or E, or we can sometimes write shall, whatever you are comfortable with, like A cos kx minus omega t. We can write it as the A sine kx minus omega t also. A cos kx plus minus vt. A cos 2 by x by lambda plus minus t by tau. Tau will be the time period. A cos 2 by kappa x plus minus mu t. Here kappa is 1 by lambda, mu is 1 by time period. So this is basically this thing, different notation, and A cos 2 by mu x by v plus minus t. We can write all this equation in terms of sign also, and that would be A sine x plus minus vt is sine 2 by x by lambda tau. A is sine 2 by kappa x plus minus vt. A sine 2 by nu x by v plus minus t. So we can see that we can write wave equation like these forms. So we can write the wave equation in terms of sine and also in terms of cos. So now move on to our next thing, what professor have explained how to do it in the class. I am doing it here to show the mathematical calculation. That is how we can from Maxwell's equation. So we know Maxwell's equations that they. So basically Maxwell's equation are divergence of E is rho by epsilon naught. Divergence of E is 0. This is Cauchy's law. Then we get a Faraday's law. Curl of E is equal to del B. del T curl of V is equal to mu 0 J plus mu 0 epsilon naught del E. So in a charge free and current free region, if rho is 0 and same J is 0. So now divergence of E is 0. Take Faraday's equation and take a curl in both sides. So here you need to put some identity that curl of a electric field or any vector field is basically gradient of divergence of that field minus grad 2 square of that field. And here we can write as a this. So for a charge-free medium, divergence of E is 0. So we get this. And here from the Ampere-Maxwell law, we know curl of B is mu naught J plus mu naught epsilon naught del E del D. So for a current-free medium also, this is 0. So we get to mu naught epsilon naught del square E del D square. So this is the equation for the equation for difference. And that's that we need to start with the part of the Faraday Ampere Maxwell law. Faraday Ampere is Ampere Maxwell law. So for that, take a curl at the both side of that Ampere Maxwell law. And we have already seen that for charge free and current free medium, J is 0. Similarly, it would be gradient of divergence of V minus del square V. This can be written as so this is 0 in any medium, so that would be and you know curl of V is minus del V. So this will give the equation for the magnetic field. So we all know that light is a electromagnetic wave, but still we only bother about electric field, and it's not like we deliberately cancel out the magnetic field. It's because the strength of the magnetic field is very low compared to electric field, and also that our eyes or any detector is more like sensitive towards the electric field. So that's why we only bothered about electric field equation when we discuss about light and all those things. But there is also a magnetic field, and same as electric field, magnetic field also with the wave equation. So that's how we get the electric field and electric wave equation of electric field and wave equation of magnetic field. Now let us discuss some mathematical problems, and for this week's what have been taught, these are very preliminary ideas around waves, so the examples are very easy and very simple. So let us start with a very basic example. So if the sun suddenly stopped, turned off, how long so the basically know that the light from the sun took some time to reach Earth. So when the sun will be off or turned off or it will die, seemingly, so we will not know that instantly. It will take some minute. So basically we know what is this. That is distance by velocity. We call basically sun to earth distance and velocity of light. So at the back of the mind, even in a dream, we know the velocity of the light is 3 into 10 to the power 8 meter by second, and the distance between sun and earth basically 1.496 into 10 to the power 11 meter. So this thing will give us 8.32 minutes. Actually, we know that the light from the sun took 8 minutes to reach Earth. So this is the reason why it take 8 minutes. The next example is the maximum electric field strength in an electromagnetic wave that has a maximum magnetic field strength of 5 10 to the power minus 4 Tesla. So the electromagnetic field has a magnetic field strength of 5 Tesla, and we want to know what is the electric field strength. So what we know, let's say magnetic field strength is B naught, which is 5 to 10 to the power minus 4 Tesla. We want to know what is E naught. So we need to know our formula. So that formula will connect magnetic field to magnetic field. So the formula is basically, I have mentioned few minutes earlier, that the strength of the magnetic field is much lesser than electric field. So basically the strength of the magnetic field is C time lesser than the electric field. So this is the formula for the strength of the magnetic field, relation between strength of the magnetic field and electric field. And please remember this formula. So we know what is B naught. So E naught will be B naught into C. So CE3 into 10 to the power 8. This thing is Tesla, and this is velocity meter per second. And after we multiply that, we will get the quantity, which is electric field, that would be in volt per meter. So this is 15 into 10 to the power 4 volt per meter. We can write it 1.5 into 10 to the power 5 volt per meter. This is the answer, that this is the maximum electric field we will get. So before dive into example 3, I want to discuss that units for electric field and magnetic field. So for electric field, the unit is volt per meter or Newton per coulomb. They are both same, and the dimension for this quantity is basically ml I to the power minus 1 t to the power minus 3. So basically we know F, force between two charges, is Q1 Q2 4 pi epsilon naught r cap r square. Electric field of Q1 will be written as like this. So basically, electric field is force by charge. Charge is basically current into time, or we can say current is charge per unit time. Charge flowing per unit time. That is current. We know this is actually force. So force is basically mass acceleration. Is L to the power minus 2. So electric field would be mL to the power minus 2 by charge's dimension. Charge is current into time. So this will be IT. So basically, the dimension for the electric field will be I to the power minus I to the power minus 3. This is the dimension for electric field. Now, we'll concentrate on magnetic field. We can write magnetic field as a Q, V, P sine theta. Sorry, this is the force of the magnetic field, not magnetic field. So sine theta is number, it doesn't have a dimension. For so dimension can be charge per velocity. So we know what is force, mass into acceleration. Q is IT, velocity is LT minus 1. So that would be N L 1 minus 1, I to the power minus 1, T to the power minus 2, minus 1 plus 1. So that would be ML to the power 0, T to the power minus 1, 2, I to the power minus 1. And the unit for B is Tesla or Weber per meter square. And always remember that same kind of units or dimensionally same kind of units get added and subtracted. You cannot subtract a Tesla from a volt per meter. You need to convert it. Let's continue with the examples. The example 3. An electromagnetic wave gigahertz. What is its wavelength in vacuum? So it is very easy and straightforward question that it is a frequency given and what is the wavelength. So we know lambda is c by nu. So this is 3 into 10 to the power 8 meter per second. By mu is 12 megahertz, it is this second inverse. So after calculation, it would be 2.5 into 10 to the power 1 meter. So that would be 25 meter. So this is very easy and straightforward question. let's go back to let's move to example 4. So the example 4 is if electric field and magnetic field strength vary sinusoidally in time at frequency 1 gigahertz being 0 right word at p is equal to 0, then E is equal to E0 sine 2 pi ft and E is equal to B0 sine 2 pi ft. When will be the field strength be E0? The next part will be when do they reach their most negative value, and C will be how much time is needed for them to complete 1 cycle. So this question might look like a very lengthy question, but basically it's a very simple question. Basically, they have asked that when the field strength will be 0. So this is a sinusoidal field, and we have seen that electric field is given as E naught, which is sine E naught sine 2 pi ft, so sine function. So we know sine function moves like this. Here it is 0, here it is 0, here it is 0, and this is the maximum field which is positive, and this is maximum field in negative direction. This is the okay. So sine has the maximum value of +1 and this -1, and sine gets 0 at 0, 180 degree and 360 degree. That's so sine 2 pi ft will be 0 when 2 pi ft is equal to n pi. So basically t will be n by 2f. So first 0 we get at t is equal to 0. So when n is equal to 0, t is equal to 0. Next, n is equal to 0 will be when t is equal to 1. So t is equal to 1 by 2 into frequency. Frequency is here 1 gigahertz. So that will be 10 to the power 9. Giga means 10 to the power 9. So this is in second. We will get 5 picosecond. This is the answer. Next, we will have a most negative value. So for that, we need sine by f equal to minus 1. So the condition for sine 2 pi f t minus 1 is 3 pi by 2 plus 2n pi. So even if n is equal to 0, we will get first negative at 2 pi ft at 3 pi by 2. So t will be 3 by 4 of. Then 5 nanosecond. In the C part, and how much time is needed for them to complete one cycle? Basically, they are asking what is the time period. So you know time period is 1 by frequency. One nanosecond, actually. Not. To next question. Number 5. Plain electromagnetic wave of frequency 20 gigahertz moves in the positive y-axis direction such that its electric field is pointed along the z-axis. the amplitude of the electric field per meter. The start time is chosen so that at t is equal to 0, the electric field has a value 10 volt per meter at the origin. So the question is, write the wave function that will describe the electric field and B is find the wave function that will describe the associated magnetic field wave. So I have already mentioned that we can write electric and magnetic field as sine wave and as well as cos wave. But here, which wave function we'll choose? That is given in a question, that the start of the time is chosen so that at t is equal to 0, the electric field is a value of 10 voltmeter. Sine always has a value 0 at the t time is equal to 0. And cos has the maximum value at t is equal to 0. So we will need cos function here, not the sine function. So we will the electric field terms of cos function. So the cos function will be equal to E0 cos kx minus omega t. And it is also given that electric field is in z-axis and the wave like occurs in the y-axis, and the electric field is in z-axis. So here it would be k, and this will be y. So now we need to know what is k, which is 2 pi by lambda, or we can say 2 pi f by c. So here frequency is 20 gigahertz. So 2 pi 2m 10 to the power 9 by 3 into 10 to the power 8. So first we need to calculate the omega. So omega will be 2 pi into 20 into 10 to the power 9. That per second will be 418.7. That per second, and this is will be 418.7 rad per second by 3 into 10 to the power 10 meter by second. This okay, sorry, to 10 to the power 11, and that is 1.256 into 10 to the power 11 by 3 into 10 to the power 8, and this unit will be rad per meter. So this is will be 418.7 rad per meter. Usually we write K in units of cycle per meter. So basically one cycle per meter is equal to 2 pi rad per meter. Here we have given the unit as rad per meter. So the electric field would be, and you know the maximum value of the amplitude of the electric field is 10. So this will be 10 cos K is 418.7, y minus omega is 1.256 into 10 to the power 11 t direction of set. And the second thing will be P naught cos K y minus omega t. And if the wave is propagating along the y-axis, E is along the z direction, B will be along the x direction. That will be 10 cos K is 418.7, and then y minus omega is 1.56 into the power 11. E will be x. So the electric field is 10 cos kz ky minus omega t, and magnetic field is, sorry, here the magnetic field would not be the 10, it would be E naught by C, which is 10 by 3 into 10 to the power 8 cos 14.7 y minus 1.256 into 10 to the power 11 t x cap. So this will be 3.33 into 10 to the power minus 8 cos of 418. That will be the magnetic field. So this is the electric field, and this is the magnetic field. So move to example 6. So the example 6 is the electric field of an electromagnetic pulse traveling in vacuum is described by the following wave function. As E is equal to 5 volt per meter into cos kx minus 6.00 into 10 to the power 9 second inverse of hours plus 0.40 J. So where K is the wave number in rad per meter, X is in meter, T in the second. Quantities. Amplitude, frequency, C, wavelength, D, the direction, of the travel of the wave, and E, the associated magnetic field. So from the equation, equation is 5.0 per meter also of Ax minus 6.00 put into 1 second inverse E plus 0.40 J. So electric field is in y direction. Here it is say Kx. So wave is propagating in X direction. So magnetic field will be in Z direction. So if we compare with is equal to zero also x minus omega to the theta. So you can write E zero is 5.1 meter. Omega is 6.00 into 10 to the power 9 second inverse. Lambda is given 3.14 into 10 to the power minus 1 meter. No, sorry, lambda is given, we will like calculate the lambda. So E naught is given, omega is given, and initial field is 140. So the omega is given, frequency it will be omega by 8 pi, and that will be 0.55 into 10 to the power 8 hours. So lambda would be C by F, that is 3 into 10 to the power 8 meter per second, and this is second inverse 0.55 into 10 to the power 8 second inverse. So lambda would be in meter, and this would be 3.14 into 10 to the power minus 1 meter. So the amplitude is 5.0 volt per meter. Frequency is 0.55 into 10 to the power 8 hertz. Omega is actually it is 9. Lambda is 3.14 into 10 to the power minus 1 meter. Now the travel of the wave I have already stated by the direction in x direction, and the E is the associated magnitude of magnetic field. So for that E, we know B is E naught by C. B naught by B naught by C. E naught is the 5 volt per meter. This is 3 into 10 to the power 8 meter per second. So we will get magnitude of the magnetic field is 10 to the power minus 8 Tesla. Seven. Now, 7 is remember the direction, the electromagnetic wave traveling towards northward at 1 instant. Its electric field has a magnitude 6 volt per meter and points eastward. What are the magnitude and direction of the magnetic field? Field. So the magnetic part is the easier part. We know this is 6.0 by 3.10 to the power 8 Tesla. That would be 2 into 10 to the power 8 Tesla. Direction. So direction, we have travel direction, no direction, E field direction, eastward. So using right hand rule, we need to know what is the direction of B. So if you the direction of the B, it would be the downward direction. When you will like check that in the via right hand that you move the right hand from like E direction to B direction, eastward to downward, you will get like you like diagram. This is east direction, this is north direction. And you can see this direction is downward direction. When like this is my right hand, so this is the eastward direction electric field. This is the downward direction, you can say magnetic field. So from east to downward, we like curl the fingers. So this is the north direction. Yeah, this is the east direction. This is the north direction, or you can say this is the east. So from east to downward direction, we will be in this direction. So we'll get the north direction in the upward direction. So this is how we can get the direction of the B field. Now let's move on to the example 8. The electric field of an electromagnetic wave is given by so 0 minus 3 whole per meter sine 2 pi x per 80 meter minus 2 by 6.0 into 10 to the power minus 8 second. Right there, so it might fit another power. So I have previously written a form of wave equation which is E naught sine 2 pi x per lambda minus E by tau. So we compare this general form of the form given with the E naught is 6 and 10 to the power minus 3 volt per meter. It is 6.20 to the power 8. To 10 to the power minus 8 to the power minus 8 Tesla, which is 2 into 10 to the power minus 11 Tesla. To 10 to the power minus 11 sine okay. Because it's in the direction. To the Z direction. To the pointing vector. So magnitude of the pointing vector. So we know pointing vector is 1 by mu naught E plus V. So if we want to have the magnitude, so that would be E naught by mu. So it is mu naught. So putting the value of E naught mu, you get 9.55 into 10 to the power minus 8 watt per meter. So those are kind of examples where you are given electric field. You can um, reduce it to the magnetic field. Magnetic field is given. You can get back to the electric field. This kind of example. Now we will move some different kind of example. We see if some wave equation, if some equation is in wave equation or not. So the wave equation is given by is 3 by 10 x minus 50 square plus 1. Show if this is a solution to the one differential equation. So for that, this function needs to satisfy the wave equation. Is del square psi when x is square is equal to 1 by v square del square psi del t square. So first we calculate del psi del x, which will be del x 3 10 x minus b whole square plus 1. So please read the differentiation very carefully. In 3 into 10 x minus b whole square plus 1 minus 2 into 20 x minus b. This is resident x. X minus b whole square plus 1. Let minus 160 10 x minus bt whole square plus 1 to the power 2 x minus 50. Now, we need to calculate the x square. That would be 10 x minus bt whole square plus 1 to the power 3 minus 15 to x minus 50 minus b. Here x minus bt was constant and so this was the del psi del x. In the first term, this should be constant. We differentiate this term. In the next, half, we to this part constant and x minus vt will differentiate. So that would be 60. Then x minus vt whole square plus 1 whole square. Now we want to calculate Scheidel T. So differentiation will be the same, but instead of x, it would be with respect to t. So we need to write this differentiating with respect to t. So here we had a constant coefficient b, so we need to take the account. So 3 x minus bt whole square plus 1 minus 1 3 x minus p whole square plus 1 minus 2 into minus 2x minus bt. So you can write it as, again, this thing is a differentiation of 10x minus bt whole square plus 1. You can write this thing like in a simplified form, that it will 6 cx minus vt 10x minus bt whole square plus 1 minus 2. So we are differentiating in this step, answer will be so now is to show right in this where we get minus 2t whole square by 10x minus vt whole square plus 1 with 3 minus 60 square 10x minus vt square plus 2 whole square. So that is basically this word included for Scheidel exists. So if we so this is basically so the Scheidel exists for 21 with this so the function is the equation, and you don't need to do that in the question, but here I want to show you the shape of the output. So this almost so shape the way this needs to be symmetrical and cannot get the symmetrical function, but this is the symmetrical and that's how the it moves this direction. But even like 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 the other equation from the function. Uh, so and doing this to bring about the previous system sinusoidal. So it doesn't come really close or sine thing, but it is a wave equation. It does move. It's a traveling wave. Now, if we, for example, okay, uh, in the black laser puts out a beam of 1.06 micrometer electromagnetic radiation in vacuum. Determine the term width. Frequency. It's temporal width and see its spatial frequency. So the MDI laser put out a beam of 0.06 micrometer in vacuum. Now to decide, calculate the temporal frequency, temporal period, and spatial frequency. So lambda is given 1.06 micrometer for the temporal frequency, which is frequency by lambda. So 3 into 10 to the power 8 to the power 7 and that is 10 to the power 6. Okay. That will be from 8 to the power 40 hertz. This is the temporal frequency. Now we need to calculate the temporal period, which will be basically so that we 3.55 into the minus 15. This is for hertz or 1 by hertz, so that would be second. Or we can say it 3.55 into second, and C is the spatial frequency. So spatial frequency is given by 1 by lambda, which will be and only 1.6 centimeter per 6 meter. Plus 10 to the power 3 meter in yours. So that is how waves per meter. So move on to example then. Sorry. So consider a function psi x t. Sorry, to psi y t equal to 0.040 sin 3 while 6.0 plus t 3.0 into 10 to the power minus 15. Where everything is units was the expression of the form of the frequency determine the frequency wavelength amplitude and direction and also speed. So I have written some form of wave equation at the beginning of the class, and one of them was 1 sine 2 pi x by lambda plus t by tau. Lambda is the wavelength, tau is the time period. So if we look at this equation, it is basically the same form of equation. And also, it is the function of x minus 3t. So, so this is 0.40 sine 2 pi y. Here, instead of x, it is y because the wave is propagating in y direction. plus D deposited and then 50. So first, what is the frequency? So the frequency is frequency is 1 by tau, which would be 1 by 2 into 10 to the power minus 15. This will be 5 into 10 to the power 14 hertz. This is the frequency. So this is the frequency. C is wavelength. So wavelength is physical is, which is 6.0 10 to the power. Yeah. And the amplitude is 0.0. You can see that this is the amplitude. And the part of the direction of the propagation, which I have already mentioned, this is in the Webber's directive. Propagating in the y direction, so that is y in the expression, it is y, and this is positive instead of negative, so it is propagating in the negative y direction. And the F was speed. Speed is V is equal to lambda. So that is 5 into the power 14 or into 6 and the one is 7 meter. So it is these three 1 into the power meter per second. So this is the solution of all the parameters they have asked. Now, move on to example 12. So we're propagating with at time t is equal to 0 can be expressed in minutes as shine line 0 equal to 0.0 cos pi by balance Oops. Negative direction. Phase velocity to second. Write an expression for the wave at the time of 6 seconds. So basically the wave equation is given. It is for t is equal to 0 and we need to write the wave equation is equal to 6 seconds. So we know that it is given as in which is a meter. Also, so what is when chi is given, it is a meter. When E is given, it will be per meter. When A is given, it will be in meter. 5 y by 2.0. So we can like where it is pi. So basically, and by 2. So it is in the form of A cos 2 pi into y by lambda plus minus t by tau. So here A is 1030 meter. So shall was 0 is 1030 and lambda from here. So you make a conclusion from this that lambda is going to you need to write it in proper form. So you write in force to the y by force and the force 4 is the lateral length. Lambda, that is lambda by tau. So tau times v will be lambda by v. So the velocity is given, that is 2 meter per second, and after is 4 meter. So this will be 2 seconds. So at time t, psi will be y comma t will be 1030 meter cos of 2 pi y by 4 plus t by So that t equal to second, y equal to child would be 0.030 meter cos 2 pi by 4 plus b. That would be the answer. So now we will discuss our last example. So an electric of a particular electromagnetic plane wave can be given by the expression E equal to 100 volt per meter J to the power I K Z plus omega T. What is the amplitude of this relation of Z on my version of the wave travel conservative electric travel. If speed of the wave is 18 to the power 8 meter per second, and lambda is 500 and 1.36. So now it is convertible meter to the power IKZ plus omega. What is the amplitude of the wave? electrical is 100 voltmeter. So in what direction the wave travel? Kz. So we are in the z direction. The wave travel basically. Because u can be written as v naught before I k dot r minus omega. So q by r is equal to k x plus q by y plus q z z. So we don't have any example of this c that is a c question and it comes as because it's being travel in z direction. But say question is what is the direction of E? The direction of E is in y direction because this is given. So it can be given in positive y or negative y or both. Okay, here it is given plus, so it will not like travel in positive y direction, so it is traveling in the negative y direction. So d is if the speed of the wave is 3 into 8 meter per second, or find its frequency. So frequency would be c by lambda, or here I have written c, but it is actually v because I did it like speed of light. So put this thing and it's lambda minus 9 to the second was of ours. So this is 6. So these are the basic example of wave equation. And also remember that why the unit dimension analysis and the how the wave equation can look with cos function, sine function, sum function, all those things. And another thing is to remember why wave function follow the superposition principle. So these are the basic things have been discussed in the actual theory has been discussed in the class by the professor, and I am giving you some examples, and with the help of these examples you can follow these examples and solve the 8 questions given in the assignment. So basically that's what is it? That is for today's class, and we'll discuss some other problems in the next class. Thank you.